takes the lowest, and that the resonant frequency, at the resonant frequency, that's when you get the leftovers. So there's one frequency, the frequency such that omega L equals 1 over omega C, and that's what you get as the resistor in an RLC circuit, and that's why it's a tuning circuit. Because by changing the L and C, you can change which frequency goes to the resistor. And that's how a radio tuner works. I don't have the net right now, but old-fashioned radios that used to sit on a tabletop that had a big knob, they had a capacitor with moon-shaped plates, so that if you turn the knob, you could cause less of the plates to overlap, making a small capacitance, or more of the plates to overlap, making a larger capacitance. So each person on the family farm, or wherever they were, would be carefully adjusting the capacitance of their capacitor until they could listen to the radio. Then what would happen is, if it was rainy outside, then the air between the capacitor plates would change its dielectric constant, meaning the capacitance would change and they'd have to go and fiddle with the knob. So on those old-fashioned radios, people were always messing with the knob in order to keep the capacitance value actually being what it was, because the medium in between the capacitor was not vacuum, but it was air, and so as the qualities of air would change, you kept having to retune it. I think the question here was first and then there. No, by changing the capacitor with a fixed inductor, you could change from one radio frequency to another. So that was, quote-unquote, your radio dial. It was a knob hooked to a capacitor. And then somebody set the range of possible frequencies. For AM radio, what's the range of frequencies?
500%.
About 800,000 hertz to about
16,000.
Yeah. And those are your radio stations, right? If you listen to radio station AM 880, it's 880 kilohertz. And if you listen to 92.5 on your FM dial, 92.5 what? Not kilo, megahertz. And it's not that if you have lower frequencies you have to amplitude modulate, and if you have higher frequencies you have to frequency modulate. It's just an arbitrary choice that somebody made. That from this frequency to that, the consumer will purchase a radio that expects the signal to be amplitude modulated, and from this other frequency to another, the computer will purchase a radio that expects that the signal is frequency modulated. So next question is here, then over there. Yeah.
So the values in darkness just 1 over omega squared C.
Yes.
And is that the same thing like if it was L circuit? Again, the capacitor is 1 over omega squared.
Yes. Yes. That will still be the formula for which frequency is resonant. Now you can drive a circuit off resonant frequencies, because when you have your radio tuner, every radio station is coming in your antenna. But only one gets through. This is the one that gets through. Okay? Yeah. What? Filter cleans out noise. And I can give you 2 examples. One was my car when I was in high school. Your car should have an electrical system with 12 volts DC. But in the electrical system in my 1974 Pontiac Le Mans with a 350 cubic inch 8-cylinder engine, the spark plugs were making little variations of the continuous 12 volts. And when I changed out the factory radio for a much better radio, those little surges in the 12 volts as the engine was running caused static to come through my speakers. So what I knew was that DC voltage is 0 frequency. So I wanted to have a low-pass filter. So I went behind the dashboard and I added a low-pass filter that I bought commercially. It wasn't strong enough, so I made it a stronger low-pass filter, and then the noise disappeared out of the radio. And then in another application, I had a student who bought a preamplifier commercially, and he was going to send it into a circuit to amplify it, and he found, oh no, the worst thing possible. The little blips were there, but they were riding as little millivolt fluctuations on something that was up at 12 volts. What is he going to do? how can he amplify that? Because it'll amplify the 12 volts. And so I told him, put a capacitor in series. He said, what? Put a capacitor in series. I taught your freshman physics. I did for the students. Put a capacitor in series. Tell me what happens. So I put a capacitor in series. The 12 volts was completely gone. But the little blips that were the signals were there completely and entirely. Why? The 12 volt is a DC signal. It's zero frequency. It all goes to the capacitor. And by putting his circuit in series with the capacitor, his circuit was the resistor and got only the high frequencies. And the 12 volt DC was totally gone for his circuit. Everything was cool. Okay. Everybody follow. So, the other final thing is, if you look at the motherboard inside your computer, you're going to find that there is always a capacitor near every chip. Because every chip expects to be running from a DC voltage. And because there are wires running all over the motherboard and your clock frequency and you're continually accessing memory, there are fast signals going all over the place. And your DC voltages can get disturbed. So right next to every chip, you put a capacitor. So that the capacitor will suck in the low frequency and that the chip will be running on DC voltages as promised. And if you went into your computer and you desoldered all the capacitors and you turned it on, it would probably run for a few minutes before crashing. But you like it to run longer than a few minutes. And so the capacitors are acting as low-pass filters. Okay, everybody with me? All right. So move on to problem 2, and let's see what it says.
I know how to do it.
Do you want to ask how you put this?
Yes. Hey, I'm sorry. How did you flip the image?
I had to download something else. I downloaded a different program.
I was just trying to figure out if I could flip the
Okay, shown below is an RL circuit driven by an AC power source. Let the resistance be 5 kiloohms and the inductance be 3 millihenries. The voltage source will have an RMS voltage of 10 volts and a frequency of 5 kilohertz. Everybody follow? Okay, then it says, what's the magnitude of the impedance? What's the phase of the impedance? What's the peak current? What's the RMS current? What's the phase of the current? What's the peak voltage on the resistor? What's the RMS voltage on the resistor? What's the phase of voltage on the resistor? What's the peak voltage on the inductor? What's the RMS voltage on the inductor? What's the phase on the inductor? Agreed?
Yes.
Okay. Now at this point we'll be going a little faster. Okay, because we've seen it all, and I think we're starting to get the rhythm of these kind of problems. So, here we go. How would I find the total impedance? These are elements in series. So the total impedance is? The sum of one plus the other. So, if I'm going to add, what format do I want for my impedances? A plus IB. What is the A plus IB format for the impedance of a resistor? R. That's the easy one. R is R. In A plus IB, in C, e to the I phi, R is R. Okay? But the inductor, what is the inductor in A plus IB format? In order to get the magnitude of the impedance, what am I going to do? So that's going to be the square root of 5,000 squared plus, we need to find out omega L. How am I going to get omega L? Where do I get omega from?
2 pi
frequency. So 2 pi times 5,000 times L, which was 3 times 10 to the minus 3 What do I get for omega times L?
94.2.
Oh, really? Only 94.2?
35. Yeah, 35.
How much?
Just 35.
Oh, 30 pi, which is
Like 94.2.
94.2. Ooh. Squared. Let's keep some digits here. I'll have something to say in a minute. What do I get? 5,000 squared plus 94.2 squared.
471,239.
That makes sense.
Did you take the square root afterwards?
Yeah.
No.
4,7. It's not going to be much higher than 5,000.
Oh, yeah.
How much? 180?
5,000.9.
Oh boy.
Okay. 5,000.89.
5,000.8, yeah. 1,000.9.
What?
5,000.9? Isn't it easy?
Yeah, okay. And the answer is? Answer is? Oh.
Yeah, just make it 5,000.
What is this? Terribly wrong.
It looks ridiculous.
And the phase of this circuit is?
Zero.
Very close to zero, yes.
1 degree. Seriously?
Why did that happen?
Yeah, it is 1 degree. Wow.
Why did that happen?
Because we messed up.
Yeah. Yeah, because the resistance is huge compared to the omega L. So what this means is that so if I wish these to be more balanced, one to the other, what would I do to the frequency?
Bump it up.
Increase the frequency. If I increase the frequency, the result would be that the omega L would be about the same size as the R, and then that would make a phase closer to 45 degrees. If the R wins, the phase is nearly zero. If the omega L wins, the phase is nearly 90. By having an R of 5,000 and an omega L of only 94, the R wins. The phase is only 1 degree, and the entire impedance is 5,000.89 ohms. Just barely higher than if the inductor wasn't even there. And just barely off from being current and voltage in phase with each other. Okay, so far so good. We can carry these through.
Come do this on the test.
What?
Come do this on the test.
Don't give ideas.
This one is not as well designed as the other one. The other one was more well designed. Did you spot it being well designed? What was well designed about it? What was 1 over omega L? Oh, sorry, what was 1 over omega C in the previous problem? 106 ohms. And what was R? 120? Yeah, about the same size. If they were exactly the same size, the phase angle would be 45. And what did the phase angle turn out to be? 41. Because you just won a little bit with the resistance. If they were 50-50, you'd have a phase of 45. But you had 120 versus 106, so you had a phase of 41. Okay? Everybody follow? So, starting